Hello, everyone. My name is Miles, and I'm a marketing coordinator here at FlexPipe. Thank you all for taking the time to join us for today's webinar on the advantages of twin composite pipelines. Before we get started, please note that this webinar is being recorded. The recording will be available to all attendees after the webinar concludes. Today's session will be led by one of FlexPipe's outstanding team members, Victor Bello. Victor joined FlexPipe 2 years ago in 2022 and has been a vital part of our applications engineering team ever since. With over 26 years of experience in the oil and gas industry, Victor's expertise spans upstream operations, pipeline design, fluid flow simulation, and evaluating non-metallic pipeline performance. His knowledge and experience with non-metallic technologies makes him the perfect speaker for today's topic. If you have any questions during the webinar, please submit them using the Q&A panel in Microsoft Teams. You can access the Q&A panel by clicking the Q&A icon in the meeting toolbar. Victor will address your questions during the Q&A section at the end of the presentation. As questions come up, please take a moment to review them and upvote the ones you'd like to be answered during the session, as that is how the order of questions will be prioritized. Thank you again, and I'll now hand it over to Victor to start the presentation.
Thank you, Miles, for the kind introduction, and thanks everyone for joining today's webinar. In this webinar, we will have the opportunity to share some experience on 2024 projects that illustrate the advantages of twin composite pipelines, mainly related to hydraulic performance. Different scenarios were evaluated for each particular case to verify the technical solution and to support decision-making. We'll go first through a dual composite pipeline benefits. Then we will briefly discuss the major considerations for pipeline sizing to provide a common base background for this discussion. Today, we will focus on multi-phase flow pipelines as an example, and 3 different projects will help to illustrate the process. Why dual composite pipelines? They represent an effective solution for fluid transportation, reduce maintenance cost, fast and easy to install, and corrosion resistant. Dual composite provide redundancy in pipeline system and increased flexibility, as well as service advantages. Finally, they have hydraulic advantages that, when properly evaluated, can provide an excellent solution. Let's first talk about pipeline sizing considerations. One of the most important parameters is the pressure drop. In this case, we need to determine the appropriate pipe diameter that will be capable to handle flow rates required by the project with the pressure available in the system. This criteria is a combination of technical and economical parameters, and the goal is to increase well productivity and reduce energy consumption. For example, in the case of the flow line, selecting a pipe diameter that will allow pressure at the well pad up to a maximum during its life cycle will ensure maximum well productivity. Another important criteria is the maximum fluid velocity within the pipeline. We want to ensure pipeline integrity by limiting erosion, corrosion, and flow-related damages. When solids are present in the fluid with high velocity, this can create loss of material on steel pipes, especially in change of directions. Also, when injecting anti-corrosive products, limiting the velocity will help to guarantee the effectiveness of the treatment in the steel pipe inner wall. For composite pipelines, the attention is focused on avoiding flow-related damages. The most common approach for maximum velocity is the erosional velocity. The API RP14E formula is commonly used, but other model less conservatives are available. For the case of a multi-phase flow, the superficial liquid velocity and the superficial gas velocity can be used to estimate the erosional velocity limit. Finally, minimum velocity in the pipeline should be considered to prevent solid particles from settling out of the carrying liquid In addition, velocity that are too low on multi-phase flow pipelines will promote liquid settling, forming large slugs that can create high pressure fluctuations and efficient flows. This last aspect is very important when designing bulk lines. The following slide compares the hydraulic performance of a dual 6-inch composite compared to a single 8-inch steel pipe, even corroded. As shown, dual composites pipelines have a lower pressure drop compared with a corroded steel pipe, due to the increase of pipe roughness with time. Let's now have a closer look on flow lines and bulk lines to illustrate the process completed in each project. Multi-phase flow, oil, gas, and water, is to be transported from the well pad to the battery station. These can be achieved using flow lines or using a single bulk line for all wells. A maximum liquid flow and a maximum gas flow is expected. The pressure at the battery station is fixed to the separation pressure level. The goal is to minimize the pressure drop to ensure that pressure at the well pad do not exceed a maximum pressure. This pressure level at the well pad is very important because it will depend on reservoir and well productivity parameters and is always asked to a customer on every individual case to guarantee maximum production. In this regard, it's also important to consider not only the maximum flow rates for pressure drop calculation, but also evaluate system performance on different flow rates using the production forecast shown in the bottom left graph. The goal is to understand the pressure behavior of the pipeline with time so a cost-effective solution can be ensured. Maximum velocity limits are also considered. The superficial liquid velocity and the superficial gas velocity can be used to estimate the mixture velocity. On composite pipelines, we want to avoid flow-related damages due to changing momentum, for example. Superficial gas velocity limits are used as a reference. In the cases of steel pipeline, we want to limit the mixture velocity below the erosional velocity limit. The API 14E formula is commonly used for this task, although less conservative models are also available. Minimum velocity is also important to consider in this evaluation. Let's now review the first project. Located in the state of Colorado, this customer had planned a 10-inch bulk line for an 8 wells well pad on Q4 2024. Pipe length is 5,800 feet. Pressure at the battery, 250 psi. Maximum oil, water, and gas flow rates were provided. Additional data was requested to evaluate different alternatives for its consideration. One was the maximum pressure required at the well pad, and value provided was 500 psi. It was also requested the oil, gas, and water flow rate forecast for the well pad. This information helped to build up a well pad pressure versus time plot to help the analysis on the different scenarios evaluated. Results obtained are shown on the graph at the bottom left of the slide. Line with dots represent the liquid production forecast for the well pad. Solid lines shows the pressure at the well pad for the different scenarios evaluated, which are 5-inch, dual 5-inch, dual 6-inch, single 8-inch, and single 10-inch. As it can be seen, the dual 5-inch option provided the hydraulic results required with a maximum pressure of 450 psi. Fluid maximum velocity were found within range. The dual 5 Each option allowed an important cost reduction compared to the original plan in this case. The second project to review was in the same area, but a different well pad. A 10-inch bulk line was planned for 8 wells at the well pad. The pipeline length was 7,500 feet. Pressure at the battery, 250 psi. Maximum pressure estimated at the well pad, 500 psi. Results on the bottom left graph show a pressure profile for the dual 5-inch that exceeds the maximum pressure required. Pressure reached 524 psi and exceeded the 500 psi limit for an approximate period of 14 days. With this information, the impact of pressure increase will be evaluated, and option was finally discarded. For this particular case, the dual 6-inch provided the hydraulic performance required with a maximum pressure of 416 psi at the peak production. This solution not only provided a suitable pressure behavior on the life cycle of the project, but also provided fluid velocities to reduce sediment deposit and large slug risks. Solution provided a high operational flexibility and greater system reliability. Finally, a project located in West Texas planned to deploy an 8-inch bulk line for the well pad. Pipe estimated length was 8,000 feet. Customer was looking for additional alternatives to optimize cost. Pressure at the battery was 180 psi. Maximum pressure estimated at the well pad was 560 psi. Production forecast was provided as data for this project. The pressure profile obtained showed that the dual 5-inch was not an option for this project, as pressure reached 785 psi, exceeding the maximum required pressure for more than 90 days period. In this case, in the case of the dual 6-inch, the maximum pressure obtained at the peak production was right just in the limit, 560 psi. But the pressure profile results show excellent performance for the rest of the project life. So this option was selected. Pressure profile obtained with the help of production forecast can help to improve decision analysis, like in this case. To summarize, twin composite pipelines have a numerous of advantages that can be considered on a project layout evaluation and definition. It is very important to perform a case-by-case scenario evaluation, taking into account the specific characteristics of each project: pipeline length, flow rates, pressure at delivery point, maximum pressure available in the system. This is to ensure the alternative solutions have been properly considered. For multi-phase flow pipelines, it is valuable to consider in the analysis the production forecast to obtain a pressure behavior through time. Application engineer from FlexPipe can provide additional support to help these type of evaluations. Thanks for your valuable time today during this webinar. And now I'll pass it back to Miles.
Thank you, Victor, for that presentation. So now we'll begin the Q&A session. As a reminder, if you have any questions, please submit them now using the Q&A panel in Microsoft Teams. And you can access the Q&A panel by clicking the Q&A icon in the meeting toolbar. If you haven't already, please take a moment to upvote the questions you're most interested in having answered. We already have some questions here, so let's get right into it. The first question is, how can operators split flow evenly between pipelines?
In order to split the flow, what we can recommend is using a spool, a header with a T center and the exit evenly with even distance that will be connected to the exits of the flow lines. In this way, we can ensure that flow will be roughly evenly distributed, although it cannot be exactly split into half, but this will minimize the differential pressure drop between the two lines.
All right, thank you, Victor. So moving on to the next question. For the first case study, if all of the options work, what was determined to be the best option? What criteria was used to make this decision?
When all options were technically feasible, as this case, the criteria is economical, basically. We want to evaluate the project economic performance, considering the life cycle of the projects. This will include capital costs like installation cost, material costs, but also operational and maintenance costs. This will help to decide what option will be uh, more beneficial for the project.
All right, so we're getting close to the end of the meeting here, so I'll ask another question. What is the biggest challenge with dual pipelines?
One of the challenges that we can encounter on dual file lines is the question that we mentioned before, like trying to avoid any preferential flow on one of the pipelines to evenly distribute it, and that was answered. Another challenge is we can have in the long term some experience with flexibility issues on, for example, when we want to install, if you want to install a big facility, probably that need to be considered, all those costs when doing the economical evaluation to make sure that actually it is the best option. And finally, as mentioned before, each case had to be evaluated individually. There will be some options where the dual won't fit, but if everything is considered, we can find several cases where dual pipelines will be an excellent option. That's why it's recommended to evaluate each case individually, considering all the details on each project.
All right, thank you, Victor. So as a reminder, if you have any questions, please submit them using the Q&A panel in Microsoft Teams. While we wait for more questions, I'll ask a question here. Are there any spacing requirements between dual lines?
Dual lines will use the standard separation that we use for pipelines installed within a trench, and that will be 4 inches is the minimum distance recommended between pipelines.
All right, thank you. And the next question is, what kind of cost savings can you expect with a dual pipeline versus a single pipeline for a given flow rate?
The most important cost saving will be related to the life cycle of the project economical evaluation when you compare for dual pipelines, and this was what we got in this mostly on these 3 projects. When we evaluate the dual pipeline options, they represent better economical advantages in this case. So installation costs, material costs, and maintenance operational costs was the main advantage when this option was feasible. Again, where's the cases, there will be some cases where dual flow lines won't be an option, but if properly evaluated, we can ensure the alternative with the most attractive and economic performance is chosen after the technical evaluation. This is very important. This is very important for each project to be evaluated.
All right, thank you, Victor. So I'll ask the next question here. When modeling pipelines, do you recommend utilizing equivalent diameter with respect to total cross-sectional area of two pipes in parallel, or would you rather model 50% flow through the actual ID of one pipe?
Yeah, the recommended method will be the 50% flow for each pipeline. That will be the best approach to model the pressure drop on the dual pipelines.
All right, so thank you so much, Victor, for your presentation, and thank you all for joining. If your question was not answered during the presentation, we will get back to you through an email. Thank you all for joining us today and have an excellent day.